what I'd like to do today, if not today, today and Wednesday, but I'm only going to go for an hour, all right? But I'd like to finish it, hopefully today, I want to finish this book. You're not going to have any more homework on the book, but I'd like to go over some of the concepts that are in it. Now, if we finish it today, all right, if we finish it in the first hour today, then Wednesday, if you can, bring the other book that looks like this but says Objective-C on it, okay? And start bringing that one. If we don't finish it today, we'll finish it Wednesday. And then next Monday, we'll start on that. Now, we've got two ways that we can go here, and I will allow the class to decide, but I want to make my case first. In that cabinet, the little cabinet that you see way over there to the right, there are 6 Mac PowerBooks in there. All right, there's 10 of you in the class. One of the people who's in the class is doing the work, but he's a security student, so he's got 2 classes during this time. So in other words, there's really only 9 of you if everybody comes. And there's 6 machines there. So 3 of you would have to buddy up, or we'd have to come up with something. Or what I'm able to do, and I should watch it, I really shouldn't be taping this, is there is a way that you can virtualize these machines so that they'll run iOS on them. And that's what I would like to do. So the disadvantage is you wouldn't be using Macs. The advantage is you'd each have a machine, and if we use the Macs, I can't tape because I don't have Camtasia for the Mac. All right, we had it last year. It was a cluster going through all that. All right, plus the copy that I had was an educational 30-day copy, so it worked for the first half of the class, and then we could never get it to work right for the next half. So I'd like to do it, at least try doing it that way. And I've talked with our IT guy who has said that he'll be glad to work with me on trying to virtualize it. All right, does anybody have a problem with going that route? We can bring the other machines out, and for fall we can bring them out, and I can show them to you, and you can go in and try them, do some stuff with them if you want. Yes. Terry, I shouldn't say it because I'm taping, but he has to know exactly what's involved with this before he can answer the question. So I have found a bootleg tape on bootlegging, all right, which I have watched. It's not long, it's 8 minutes, but he has to watch and then figure out if he can do that. He said he could probably figure it out in a day whether or not he can do it. The problem is IT is working on this portal thing and everything else, and the stuff that they're working on with these projects is supposed to be done Friday. So he told me that if I can get him the information, he may be able to see if he can do it Saturday, and then come Monday, it would be available. All right. So like I said, I want to answer the question. I just don't know what the answer to the question is. My hope is that he can add it, and it can be an offshoot from the virtual desktop you already have. That's my hope. I don't know if that's possible, or if he's going to have to actually create a new virtual desktop for the 10 people who are in this class. I don't know. No, that'll be nothing like that. No. But what I'm wondering is if it's something that can be if he can shoehorn it into your current virtual machine, or if he'll have to create yet another virtual machine. The other problem with that is there's only a certain number of accounts, and he'd have to create 10 more accounts, and I don't know if he's even got that many to create. So there's a lot of it that I don't really understand. All right. Yeah, but you don't want to do that. Even non-Mac recommends that you don't do it that way. It's stuff that can be done. Plus, you can do it. You can write them in C++, and I don't want to do that because C++ isn't that popular a language anymore. It's not that it's a bad language. It wouldn't hurt you to learn it, but the majority of iOS development that's being done is being done in Objective-C, and will start transitioning over to Swift. So. All right. So I'm going to go over as much of the rest of the book. So I'm on page about 280, and I've got approximately 140 pages left in the book. So we're done with about 2/3 of it, in other words. So there's certain chapters in here that I'll talk a little bit about, and there's other chapters in here that I'll say almost nothing about. All right? This one's sort of in the middle. If you don't know this, the C programming language originally was written as a language to support Unix, not Starnix or anything else, back in the day when there was only Unix. And first there was a language named BCPL. I don't even know what it stood for. Then it became B, and then natural offshoot after B was C. All right, and that's basically how it evolved. All right, it was created by gentlemen who worked for AT&T Bell Laboratories at the time, as was C++. All right, and really, more than anything else, one of the things that made C so popular was the fact that by using things like pointers, it was an unbelievably powerful language that allowed you to do things that most other languages did not allow you to do. All right. One of the things that C allows you to do is allows you fairly easily to do operations on bits. All right. So you've seen stuff like this before. You know, let me get rid of this. Where you say int x equal 10, int y equal 13. All right. Just keep it simple like this. Make this a little bigger. All right, so you've got this, and then you come in here and you've got if x greater than y and y less than 17, for example. I'm just making this up. It doesn't mean anything. All right, but what I'm trying to tell you is this. You know that the way that C works is it does short-circuit it. In other words, this is an and. It says, is x greater than y? Well, you already know it's not by looking at this. So it doesn't do this test because there's no reason for it to do that test. All right. However, if you do something like this, then even if the first test fails, the second test is still made because it's doing it on a bit-by-bit comparison as opposed to comparing entire values. All right. The reason that I'm telling you that is when you work with bitwise operations, you're used to seeing things like this. For instance, and, or, etc. All right. But when you work with bitwise, instead of that, like I just showed you, it's single. All right. And very quickly to show you this, all right, if x is 10 and y is 13, just to show you this very quickly here. All right. So let's just say I've got 0, 0, 0, 0. Oops, those aren't zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 10 would be what? 1, 2, 4, 8. 1, 2. All right. So that would be 2 plus 8. So that would be 10 right there. And this would be 17. So when you're coming in here and you're doing an anding and an oring, when you do an and, what you end up doing is you say, okay, if they're both 1, make them a 1. If they're both 0, make them a 0. So you can look at this and you can tell by looking that's going to be 0. Does that make sense to everyone? Because there's not one column on each when they're both 1. All right? So if I did x anded with y, single and, I'd get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So that would be x anded with y. On the other hand, if I do oring, that says any time that you come in here and you find there's a 1, whether there's 1 or 2 of them. So again, we have here 1, 1, 0, 1, 1. You see what I'm doing? All right. So again, that would be x ORed with y. And that allows you to do a lot of different kind of bitwise manipulation. If you're doing system programming, so if you're doing things like creating operating systems, you do a lot of this kind of stuff. All right. For regular application programs, there's not a lot that it's used for. All right. So on the next page here, they show you the major operators on 280. Now, I've already showed you bitwise inclusive OR, which is the pipe. There's also bitwise exclusive OR. And what that is it says, okay, whoops, only match the ones where there's a 1 in one and there's not a 0 in the other one. Well, notice on this one, it's going to be the exact same. There aren't 2 of them in here that both have a 1. So whether I did an X ORed with Y or I did an X with an exclusive OR with Y, in both cases, I'm going to get the same value. All right. Now, does that mean anything? Not with the stuff that we're working with. One's complement is basically, it's how negative numbers are handled. All right. And what you end up doing is you end up taking all the zeros and making them ones, all the ones and making them zeros, and working with higher order bytes. I don't really want to go into it. It's in your book. All right. What is kind of interesting is the left shift and the right shift operator. So I just want to say just literally a couple things about that. All right. Now on 281 here, they go through the bitwise and. This is the same stuff you learned with Julie Bellman. All right. And after that, they go into on 283, they go into the bitwise OR. You've seen these truth tables before. And this is what I've just showed you a little bit ago. They use better numbers than I used. All right. And they show you the exclusive OR. Again, the difference between, did you guys go through exclusive OR in math and logic or just OR? Okay, if you look here with exclusive OR, one has to be true and one has to be false, or the whole thing's false. Whereas with a regular OR, with an inclusive OR, one can be true and the other can be false, or they can both be true. And then finally, you've got the ones complement, which just turns zeros into ones and ones into zeros. It makes true false and false true. All right? Okay, so fine, dandy. If we turn up and look on page 287 here, this, like I said, maybe this is just me. It's kind of interesting. All right? Because when you use the left shift operator, you end up shifting bits to the left. In essence, what you end up doing when you do a left shift is you end up doing multiplication. Okay? It's really the way computers do multiplication. And, you know, most people don't believe this, but when you say, what can a computer do? All right, well, it can do addition, it can do subtraction, it can do multiplication, and it can do division. Technically, no, it only does addition and subtraction. And the rest of the stuff for multiplication and division, it uses shifting. You don't have to worry about that because it's all done internal to the machine. But if you have an interest, they mention on the middle of page 287, they talk about the left shift operator. All right. And notice what they're saying here. All right. So what they end up doing with this is they move everything over. So if they change W1 and they left shift it by 1, they put a 0 in the rightmost position and move everything else over. And that 0 that's on the end falls off. So notice by shifting it by 1, it's the same thing as multiplying it by 2. And what you find when you look on the bottom of this page with the right shift that goes on to the next page, it's the same kind of thing, works that way. If you right shift by 1, it's like dividing it by 2. All right. So again, you know, you might say, well, am I ever going to need this? I mean, is it really important? It's kind of interesting. I don't know. Maybe that's just me talking and you think, no, Jeff, you're wrong. It's not interesting at all. Okay. Then I just stole 2 minutes of your life you're not going to get back. All right, on 292, they talk about bit fields. All right, this is 292 down near the bottom of the page. Well, especially if you go past the page. But it's on 292 on the very bottom of the page. There you go. It says, with the bit operators that they discussed previously, you can perform all sorts of sophisticated operations on bits. Am I right in assuming you know what a bit is? That any character is made up of 8 bits. Those 8 bits together constitute a byte. Bit is short for binary digit. So it's going to be a 0, meaning that that bit is off, or a 1, meaning that bit is on. All right. So they do mention this on the bottom of the page and the top of the next page. They go through a couple programs, but there's not really anything of any significance, but at least you've heard the concepts. All right. All right. Moving up all the way to page 299, which is the beginning of the next chapter. Am I right in assuming that now everybody understands how to create a constant in C? Am I right in assuming that? Remember that when we get into Objective-C, Objective-C is a superset of C. In other words, if you wanted to, there wouldn't be a reason to do this, but if you wanted to, you could write pure C programs and compile them in an Objective-C compiler, and they would work just fine. Okay? But again, this is the way that most people create constants, are like this. Pound define, then the name of the constant doesn't have to be in uppercase, but by convention it usually is, and then its value. All right? You do that typically you do that at the top of the program. You don't have to, but typically you do it at the top of the program, and there's no semicolon at the end. So they've got a real simple program with this on the next page. And again, this kind of shows why you use it. All right, say answer equal yes. Supposedly, at least, it makes your program a little bit more intuitive to people who might be using it. You may or may not agree with that based on the example that's here. Again, the pound define statements appear first in the program, but it's not required. They can literally be anywhere in the program. All right, but it's convention that you always see them at the top. Okay, and I like Quotient's books. You may or may not, but you know, I'm looking at what he's done here, and I kind of don't understand it just because of the fact. If you look at the example here that he's got in program 13.2, that's on page 302. Okay. You can see it's pretty obvious what he's done. Come on, click. What he's done right here is he's creating a constant that's called pi, right there, and he's giving it the value of pi to like 8 or 9 decimal places. Nothing at all wrong with doing that, except C already has a built-in constant that's called math underscore pi. So although I think he did this to show you it could be done, there would really be no reason to ever do this, because you already have a constant that's been created for you. In fact, he even mentions this down on the bottom of the page. I guess it's m underscore pi. So if all you do is include the math.h header file, you know, you've got that constant for you already. All right. He mentions again that typically the reason that you end up doing this is for readability. All right, because it's much easier for people to see stuff like pi as opposed to 3.14159248735 or whatever the heck it is. All right. Okay. C was one of the first programming languages, if you've never heard this, that was designed to be completely portable. In other words, in fact, what I did was I did grab a couple of the old programs that I had done. I don't have many more, but when I was at AT&T, I grabbed them, and when I went over to Woodward Governor, just for the hell of it, there was nothing proprietary. I tried to, literally, it was a different compiler, so I had to recompile them, but I made no changes. I recompiled them and ran them, and it worked just fine. So it's compiler dependent, all right, because what the compiler does is it sets things like, this is how many bytes long an int's going to be, this is how many bytes long a float's going to be, etc. But the idea with portability is C is designed to be a portable language, that you can write it once, and you might have to recompile it in different places, but it should work on all of them with little to no change whatsoever. All right. Now, that may not sound like a big thing because many languages are like that now, but man, back in the 80s and whatever, very few, if any, languages were like that. All right. All right. They even mention you can do something like this. So they're creating a constant, and the constant is called 2 pi, but notice they're giving it a formula. Okay? And just so you know, if we look at that example that's here, let me get that out of the way a little bit. But if we look here, remember earlier he did this. He said pound define pi, and then he gave it a value like 3.141159456 43. I don't know what the rest of it is. I don't care. And then what he's saying is you can say pound define 2 pi. All right. And then you can say 2.0 times that, which kind of begs the question, can't you just go like this? Pound define 2 pi, and can't you just have it say 2.0 times pi? Yeah, you can do that too. Not only that, I'm going to tell you this, and I just want you to see this because this might surprise you. All right? That actually works. Even though we defined this one after this one, it still works because the way the compiler works is it goes up to the top and it grabs everything, and it just basically reconciles it all at one time. So as long as you have defined them both before you try to use them, which is going to be down in your C program someplace, the order in which you do those doesn't even matter. And he mentions that in the book also. Okay. Where this gets really, for lack of better words, quirky is if you turn up to page 308 and you look at this. This is a great example he gives about a third of the way down the page. Is he says that you can sit there and define yourself the equivalent of a macro right here for leap year. All right, you can put that inside of code and then just say if is leap year. Now that's actually pretty nice to be able to do something like that. All right, where this gets a little quirky though is when you create this and you start giving it arguments. All right, I'm on the bottom of page 308, and the author starts showing you this. It says if is leap year can be defined to take an argument as follows. So you've got pound define is leap year, y, and you've got the same kind of stuff that you showed before. All right? And the author says, unlike a function, you do not define the type of argument y. So you can do that, and it works just fine in that case. But when you start having a lot of different arguments, it ends up breaking down a little bit. And this is what I want to show you. I'm going to turn up a page or two, I guess the next page on 310 here. All right, first the author talks about this, and he says, I want to pound define my own function that's called square. I want to be able to pass it in a value, all right, and I want it to return that value times itself. Makes sense, right? All right. And he said, okay, so you want to do this. And he said, although you might want to do that, that's really not what you're going to get. Because what if you end up putting it in like this? You've got some variable plus 1. You think it would do v plus 1 times v plus 1. But it does it like this. It takes it out of the parentheses. So it says 1 times v, and then it adds v to it over here, and then it adds 1 to it over here. Because it strips the parens off if there's only the single set of parens. So if you want it to work, you've got to actually do it like this. The idea is if you've got arguments, the arguments themselves should each be enclosed in their own set of parentheses. And if you remember that, you're golden. But one of the reasons that C was a popular language and has been a popular language is a lot of other software, things like, for example, Excel, when they went back and they allow you to do things like macros. They were stolen from languages like this. All right? And it's the same kind of idea. A lot of times what developers do is they end up writing routines that they use a lot, and they create simple macros out of them. They put those macros into a header file and then include that header file in their program so they're able to use that stuff. All right. Another thing you can do with C, and this is fairly new, not all versions of C support this, all right, on 311, variable numbers. See that right there? Halfway down on the page on 311. Pound define debug printf ... What the heck does that mean? That means that you can pass 0 or more things into it. You may not know until runtime how many arguments you're going to have to pass in. This will accept a variable number of arguments. That doesn't seem like a big thing today because, for example, we've talked about this a little bit in PHP. PHP will take a variable number of arguments. Yeah, but C, when it first came out, would not allow that. It would blow up if you tried to do that. All right, so it's a fairly recent, fairly new C invention. All right, page 312, the pound operator. This is out there. It says if you place a pound sign in front of a parameter in a macro definition, the preprocessor creates a constant string out of the macro argument when the macro is invoked. What? All right, so what they're saying is if you do this, it's equivalent to doing this. I have never seen this. I find this unbelievably hard to even understand. All right, I don't know why on earth you would use something like that, but it's a thing that's available to you. Okay, I'm just going to leave it at that. If you like the fact that you can use a single pound sign, you can also use a double one. As it says there, it's used in macro definition to join two tokens together. I have never used this. I've written more than my share of C macros, and I've never felt the need to do it this way. All right. We all know what pound include is, and we all know the difference between pound including like this and pound including like this. Am I right in assuming that? When you pound include with the double quotes, that's your file. That's a local header file. When you pound include inside of the angle brackets, that's a system header file. All right, and that's what they mention on the bottom of 313 and going on to 314 and going on to 315. Okay? I probably mentioned this to you before, but just in case I did not, so you're used to doing stuff like this. Pound include stdio.h. Okay? All right. What you're going to see, that the biggest difference when we get into the Objective-C stuff is in Objective-C you don't include, you import. So what's the difference? Include, if the file's already been included, it includes it again. Import checks to see if the file has been included already. And if it is, if it has been included already, it doesn't include it again. That's one of the things that Objective-C changed from C. Was they said there's too much code bloat because people keep including the same file sometimes, or the same headers 5, 6, 10, 100 times. And they said that's ridiculous. All right, so that's one of the things that they changed. Now, when you do this stuff, you can do it conditionally. You can write code to put in your header files. What does that mean? You can use these. You can say basically if defined or if ndef. So a lot of times what you'll see with this is you'll put pound if ndef, which means if you haven't defined it before, then define it. So you'll have that inside of pound if ndef tags. All right. So you can conditionally compile stuff to say, hey, the way that this is almost exclusively used is a lot of times people have like a Boolean flag that's called test. And if test is set to 1, that means you're in the testing mode. So if you've got a bunch of printf statements in there, all right, print them all out. But if test is set to 0, you don't want to print them out because you're in development mode. All right, and that's typically how this is used. Not only can you define things, but if you've defined them, you can come back in later and you can undefine them. All right. You see this a lot in systems programming. When I was back doing some systems programming, I had all sorts of pound if defs, you know, etc. A lot of them. All right, jumping into chapter 14 on page 321. First thing the author talks about are enumerated data types. We've talked about these before in other languages. All right, we worked on these a little bit in the C# class. All right, now if you weren't in that class, granted you didn't have them, but we've talked about them in Java also. So it's enum. So right now, what is this doing? This is setting up a new data type right here. The new data type is called primary colors, and it has 3 possible values: red, yellow, and blue. Red has got the integer equivalent of 0, yellow has got the integer equivalent of 1, blue has got the integer equivalent of 2. So we create the enumeration right there, and then we make my color and Greg's color, I guess, are both of type primary color. That makes sense? So it's a way you can create your own data types. Okay. They've got a better example of this on page 323, where the author comes in with an enumeration right here. And he's got enum month, January equal 1, so February is 2, April or March is 3, etc. Then he comes through here and he uses a switch. All right, so a month is of type month, so it can only have those values. All right, kind of nice. Now this is a simple example that doesn't handle leap years, but it's fairly simplistic too. All right, you may or may not remember, but when we talked about structures, this was a while back, but when we talked about structures, one of the things that I mentioned with structures is you can use what's called a Typedef statement with your structures. All right? As it says, C provides a capability that allows you to assign an alternative name to a data type. So if you do this, oops, okay, it's not going to let me do that. If you come in there and do this, if you say typedef int counter, that means counter now means the same thing as int. So you might want to typedef something just because you don't like the words int, float, whatever. So one that I've seen already is people typedef, for example, decimal or dollar to be of type float. So they can say that their variable is of type decimal or it's of type dollar type of thing. All right. You don't ever have to use it, but it's another thing that's available to you if you want to use it. Where this is almost exclusively used, though, is like this. All right. Typedef struct, and you've got all that's in there, and you put date. By saying that, you can say date birthdays. If you don't typedef it, you have to always say struct date. But by putting the typedef in there, it's really typedef struct date. All right. So what you're saying is instead of saying struct date, you can just say date. It's a little bit of a shortcut. If you say, well, that confuses me, you know, and as I've said before, not to be funny, then don't use it. All right. And the last thing they talk about in this chapter are data type conversions. On the bottom of page 327 and on the top of page 328. And hopefully the stuff in here makes sense. It says if you've got an X and a Y, all right, and if either X is type long double or Y is type long double, if anything else is below it, it automatically gets converted. See, in other words, C likes to work with apples and apples, not apples and oranges. If you've got one that's of type double and the other is an int, then the other is converted to a double before the calculation is done. If one is a float and one is an int, then the int is automatically created or changed over, converted to a float, and then used. And then all that stuff happens on the right-hand side of an equal sign. So when all that stuff happens, basically all of it, you're just working with copies. All right. As it says, if one operand is of type bool, char, short, int, bit field, or an enumeration, all right, and the other one is not, then they're both converted to ints. That's why when we looked at that enumeration before, when you had primary colors, and I told you that yellow was 0 and blue was 1 and red was 2, that's what it works with, are just the integer values. All right. And long, int, etc., the same kind of stuff happens. Okay. All right. So that's it for chapter 14. Chapter 15, almost exclusively, just so you know, is a Linux chapter or a Unix chapter. And they talk about how you compile C programs under Unix. We're not using Unix, so I can skip just about all of it. The only thing I wanted to mention, all right, is if we turn up all the way to the bottom of 336, we'll go up a few pages here. This is stuff we talked about earlier, which you may or may not remember. This thing that's called communication between modules, and they talk about external variables. All right, and we go to the next page here. Remember when I talked about this in class? Anybody remember this? Oops, sorry. This line right here. If you see something that looks like that, extern int move number, what that literally means is it'll be at the top of your program. That means that move number has been defined in another file someplace. And you're telling the compiler, you go out and find it. Okay? It's a way that you can share the same variable that is the exact same variable, not a copy, but the same variable among multiple source files. Yes? No, there's, not that I know of, no. No. Yes. Yes. If you knew, for example, the stuff that I used to work on, I mean, I was amazed when I saw some of the stuff when they put it together. There were hundreds of thousands of files. All right, and the compiler was so optimized that it knew how to go through and find them fairly quickly. All right. Just a couple more things here on page 339, and that's actually it for this chapter. But if I turn up to 339 here, they talk about static versus extern. Okay, remember what static means. Or maybe you don't remember what static means. All right, if I write myself a real simple little C program, and it's going to be very simple, okay? So I'll leave that in there, that include statement. And I'll come through here and I'll have int main int, okay? Int main, there. And I've gotten here int x equals 4, int y equals 5, and I've got in here static int count equals 0, all right, and I come in here and I'm going to call int z equals, you see me write this function a lot of times before, x, y, and I'm going to pass in here count also, all right. And then I come back in here and I want to do two things in this function, very short function. So this will return what? An int. And what we want to do here is we want to say return x plus y. But before we do that, we want to say count plus plus. All right. In fact, we don't even have to pass it in here. We can do it up here. That's cleaner anyway. All right. So I'm going to call add 2, and then when I get done, I'm going to say this: count plus plus. All right. And this may or may not make any sense to you, but play computer for a second. All right. So we've got two variables here, and we've got another variable here. Then we're saying add 2. So z is going to equal 4 plus 5, right? It's going to keep doing it. Well, let's say that I put this into a loop, this int z. So let's say I wanted to call add in for some reason a bunch of times. All right, so I'm going to say here int z equals 0 for right now. And I'm going to write a quick little for loop. For int x, I got it written x already, int a equals 1, a less than or equal to 10, a plus plus. All right, so I'm going to go in there and I'm going to call this function 10 times. And after every time that I call it, I'm going to print out printf answer is %d z. Okay, so what that's going to literally print out 10 times is z equals 9, z equals 9, z equals 9, 10 times. Okay, so you might say, fine, why would you want to do that? I wouldn't, but I'm trying to show you something here. And that is this. When I do this and I run through this, now I'm going to be adding 1 to count every single time. So when I get done and I fall out of here, okay, when I fall out of the for loop, if I say printf count equals %d count, okay? If I do that and I keep running it and running it and running it, this is going to retain, this is a crummy example, but this is going to retain its value. What static does is it says the next time I come in, and if I call this routine again, so let's say I call this again, and I called it again, and I called it again. If I keep running this 10 times, count's going to equal 10. Then if I run it again, it's going to equal 20. Then if I run it again, it's going to equal 30, etc. So when you create a variable and you make the variable static, even though it's a local variable, it retains its value through different function calls. So it makes it act almost like it's a global variable, even though it's still local. All right? The explanation was better than the example was. If you write another function in here, like if I do this, count plus plus, now it's going to be 11. But what I'm telling you is if I keep calling this over and over and over again, and really what I should have done is I should have taken all this and I should have put it in something that wasn't made. All right, so really what I should have done is that add to, I should have done it down here where I had it originally. But what I'm telling you is what static does is it says when I return to the function again, have it hold the value that it used to have. So this is only initialized to 0 once, the first time it's called. After that, it retains its value from each function call. All right. Yes. Yes, you could. All right. Chapter 16 on page 347. Input, output. The key thing to realize when you come in here and you start talking input, output, this chapter is, actually it's a very important one, and it's one maybe I should have covered earlier because it talks about, for example, on 348, get char and put char. We've talked about these before. I will tell you that you will never, let me repeat that, you will never, ever, in application code, ever see a scanf and a printf. You will not see those. Not in application code. Scanf is considered evil. It's too easy to fake out the computer by putting in garbage. Plus, when you use put char and get char, what you're able to do is you're able to manipulate and look at your input or output on a character by character basis. You cannot do that with a scanf and a printf. All right? So when you really are working at a character level, you will almost always use get char and put char. All right. Then they talk on the rest of the page, they talk about printf and scanf, and they show you some of the flags. We didn't go over these very much, but if you want to make sure something is left justified or right justified when you're using this, some of the different modifiers that you can use. I'm not going to go over those. You can see them there. And they have them both for for printf rather, and there's some for scanf also. So they show you a program on pages 350 and on the bottom of the page here, and going on to page 351, where they just print out the same values all over the place, and they play with it and they format it, and sometimes they print it out in hex, etc. So you can see there's your output. I used to have people, because back when I was teaching this at the school I used to teach at, we didn't have a math and logic class, so I had to talk to them about octal and hex also. All right, and when I was doing that, it didn't take long before students were smart enough that they did some investigatory work on their own, and they found out that it was real easy to input something in decimal and then print it out in octal or hex. All right, so they were printing out whole octal and hex charts for themselves, and then I couldn't, try to quiz them anymore because they'd already written programs to do that. And you might say, well, why didn't they just Google it? Again, remember, this was back in the early 80s. There was no Google. All right. And again, turning up to page 355, they talk about some of the stuff that you can do then with scanf. Some of the modifiers, etc., that you can use with that as well. And they've got, examples on all of 356 and part of 357. All right. Then the rest of the chapter, which is about the last 10 pages or so, starting on page 361, they talk about, 351. They talk about how to work with files. Okay, and the thing is, what page is that? 357? No, I actually was on the page to begin with that I wanted to be on. It was you're right, it was 359. The idea is, if you use printf, you're printing to the console. If you use fprintf, you're printing to a file. If you use scanf, you're reading from the console. If you use fscanf, you're reading from a file. So when you preface these things that we've learned about with an F, the F means file. Okay? And that's what they explain here on pages 359, 360, 363, 364, 365, all the way through the end of the chapter, which is on page 370. Okay? All right. Turning up to chapter 17 on page 373. Miscellaneous and advanced features. Go to. Should never use it. C allows you to use the go to statement. The recommendation is that you never use it. Ever. (374), if you look at this line that's right here, that I'll try to put in purple, or in pink, right there. All right? While, and then you've got all that stuff, and notice that there's a semicolon all by itself on there, that's a null statement. That means while that's true, do nothing. Okay? There is no real null word in there in the language, yes. No, it's, the idea with a go-to is an unconditional branch of control. You're telling it, no matter where you are, go here. And the idea is you should never be unconditionally doing anything. Because what that basically is saying is there you have no choice. You should be asking a question first, and based on the answer to the question, you should be branching this way or branching that way. All right, that's all. You know, that's like saying, you know, back in the days, and maybe some of you know, I don't think anybody's was in this situation, but back in the day, you know, when it, or if we were at war right now, I don't know if we are or not, but if we were at war right now, and you were 18, and it was just taken for granted, you turn 18, that day you go down to the draft board, and that day you get shipped out someplace. That's a go-to. You have no choice. You know, and imagine if you didn't do it, they would come and get you, literally. All right, and that's why it's never recommended that you do that. All right. Back in the days, turning up to page 375, when memory was at a premium, when you create something that's called a union, it looks a lot like a structure and it acts a lot like a structure. But what it's saying is mixed can hold either a character or a float or an int. But what it's doing is it's using that amount, the amount of memory for the biggest one of those, but it can only at one time hold either a character or a float or an int. So what you end up doing with that is it allows you to store different data types in the same area in memory. It's hardly ever used anymore because memory's not at a premium the way it used to be. All right, it used to be you talked about memory in Ks, all right, not in gigs. All right, a couple more things and then we can take a break. I'm on page 378 near the bottom of the page here. The comma operator, just like in other languages, notice this. In this for loop, this says what you're doing is you're initializing two things. You're initializing I to 0 and j to 100. Since you want to do both in the same initialization operation, you put a comma in there. You can do that in virtually any language that allows you to use a for loop. Type qualifiers, you may or may not remember, but I did talk about this before. The register qualifier, that if you put register before the name of a variable, what you're doing is you're asking the system to use a special place in memory, all right, that's supposedly is closer to the actual CPU so it'll react faster. There are only a few of these available in a program, so they're typically used for counters that are going to be used a lot in a program. The problem is if the system does not have any registers available, it doesn't tell you and it just makes it auto, which means that it gets no more precedence than anything else does. A couple of other things mentioned on the next page. They talk about the volatile and the restrict qualifiers. This is on page 379 and yeah, 379. It says with volatile, it says this is sort of an inverse to a constant. It tells the compiler explicitly that the specified variable will change its value. All right. It says it's included in the language to prevent the compiler from optimizing. When it optimizes, it basically it says, you know, it does little compiler tricks. You know, you were asking about this before, Mike, but to try to make things compile quicker. All right. It's kind of like what, you know, it's not the same idea, but it's sort of like I've mentioned to you before in other classes, where you read something off the net and you go and you put it into memory how it caches. All right, it'll put it, you know, put it in memory and cache, and then it'll check, you know, basically, and it'll try to use the cache whenever it can. With volatile, what you're saying is, I don't want you to cache. the equivalent of telling the system that. This stuff is going to be changing. It's going to be volatile, which is exactly what that means. You don't see it put in code very often. Yes? No, yeah, for lack of better words, yeah. I mean, there's more going on internally than that. But what you're telling the system is don't try to optimize this variable. It'll be changing so rapidly. Don't try to pull any of your optimization tricks on it because you're going to be hurting the program, not helping it. All right. And as it says, restrict is also an optimization hint you can use for the compiler. All right. And as it says, the compiler can choose to ignore it. It tells the compiler that a pointer is the only reference to the value it points to throughout its scope. In other words, it's not going to change. So this, once you set it, is always going to point to something, and so is this. As it says, for the duration of the scope in which in pointer A and in pointer B are defined, they will never access the same value. They'll just always access something else. Again, I have never used either of those. All right. Two more things, and then we're done. All right, at least for now. Command line arguments. That's how a C program is usually written. Not the way you've been doing it, but like, come on, like this. It's not letting me, doesn't like me on certain things. I can't highlight it. There it is. So we've been writing int main void or int main with parentheses, but this is the way it's usually done. All right, notice still int main. The argc is the number of arguments you want to pass in on a command line. The argv is a pointer to a character array, and it stands for argument vector. Those are the arguments. So as they say, if you were to run a program, and let's assume that I wanted to write that add2 program that we looked at here before, but let's just say we did it all in main. So we were doing everything in main. And what we wanted to do is when we run the program, you're used to doing things like this. You type in cl add2.c, boom. And then to run it, you type in what? Add2, right? All right, that's the compile and the link, and that's the run. If you were to add things into and run them from the command line, I could call add2, and I could say 3 and 47, and it would come back and say 50. It would. In other words, these are what I want to add. Okay? If you are running programs that require information at the command line before you run them, that's how you do it. And you might say, oh, this doesn't make any sense. This is the way that almost all Unix tools are written. Okay? This argument vector, zero is always the name of the program. Always. But for example, for Linux, Unix, Starnix tools, all right, usually you run them from a command line and they expect certain parameters. And if you don't give them the right parameters, then usually you'll get an error message on the console that says, this is the name of the command and these are the parameters that you have to use. All right? So they do have their uses. All right, last thing, and it's about, unfortunately, it's several pages. And this is probably the only thing that I've covered today that if I were to say to you, I would actually go back and read this. All right? And this starts on the bottom of 383, and it really goes for pretty much the rest of the chapter. Dynamic memory allocation. Okay? And what you're saying there is you want the ability in C, all right, to allocate memory dynamically. In other words, I'd like to be able to write myself a C program, and I'd like to, while the program's running, say, oh, I'm going to do grades for this class. I've got 24 people, and boom, it would give me that amount of memory. Oh, one person just dropped. Teague just dropped. All right, so boom, now it's 23. Okay? And what you can do in this language, and this is about the only way you can do it, all right, is to use the different things in here for dynamic memory allocation. So what they're saying in here is it says suppose that you want to write a program. And as an example, you're going to be doing things. Let's pretend for a second that we are polling people. You know, we're getting their opinions on different things. And sometimes we poll 5 people, sometimes we poll 50 people, sometimes we poll 500 people, sometimes we poll 5,000 people. So we do it in iterations of 5. All right? Well, the problem is if we want to be able to use the same array for all of them, we could make it 5,000, so it would handle the biggest size. But if we're only polling 5 people, then we're wasting 4,995 storage locations. All right? But what we can do is we can use these 2 built-in functions that are called Kellock and Malik, which basically will tell us to dynamically give us more memory as we need it. It's kind of like what we talked about in the Java class when we used an array list, where you could, an array list would be a certain size and you could dynamically add to it. This is the equivalent of that in C. Kellock and Malik work very similarly. All right? But Kellock gives you whatever storage you ask for, and then it sets all that storage equal to 0 automatically. Malik does the same thing, but it doesn't automatically set the stuff that's in there. It doesn't initialize it to 0. So sometimes, as they say, a picture is worth more like 1,000 words. So you use this in conjunction with what's called the Sizeof Operator. All right. So if I want to go and add 5 new structures, then I add them based on the size of that structure, or the size of an int here. There's a size of struct data entry. All right. So you end up writing code that looks a lot like what's shown here on page 386 in your book. This line that's right here. That line there. It says, if you want to allocate enough storage in your program for 1,000 integers, this is how you do it. All right. And you might say, well, who cares? Big deal. You can realloc it basically as the program's running. This is as close as C allows you to do things in runtime as it gets. All right, because this is not a language that was set up for you to be able to do things at runtime. And as you add things, it's important that when you're done with them, you call the free function and you free the stuff up. Because if you don't, that memory is just out there, and now nothing can access it. And you get a lot of those blue screens of death and things like that. All right. So that was quick. The only chapter that's left, I'm not going to go over. It's chapter 18. No, there are 2 more. All right. Chapter 18 is on debugging, and most of the stuff that's in there is really, really simplistic, or it's in Linux. There's virtually nothing that's in there that is for a Windows-based compiler like we're using. All right. So the only chapter that's left starts on page 411, and it's on object-oriented programming. I will go over that, but not today. We'll go over that. You don't have to bring your books, but I'll go over that on Wednesday, and then we'll start on the next book. All right. So the rest of the period is yours to continue working on your homework.